let's have a look at the topic of linear approximation in calculus. So what we're interested in is if a function f of x is differentiable. Obviously, calculus is about derivatives, so if it's differentiable, and the change in x is small. Now, hopefully you know enough about these sections to know these are the two things that we're going to be needing to check. Then the change in f, the change in the height, is approximately the slope of the function at a point A times delta x near x equals a. So what does that say? Well, it says essentially use the tangent line. So let's think about that. I have some random function here. Here's my point A. Let's imagine that it's a lot of work to compute points on this function. And so I have the slope at A, right? And I want to move to the right. And I want to know how much did f change? Well, take the slope and take the distance here, the change in x, and you can estimate delta f. Now, this is really very parallel to the tangent line. Think about it. If you have this, right, you can say, well, what is delta x? Delta x, that is really x minus a. If I have some other point x here, it's the distance between x and a. And, well, what's the change in f? Well, the change in f is, I guess, f of x minus f of a, right? And can you see that this is essentially the tangent line? If I wrote this as, say, y, this is an approximation again, this is an approximation of the function, y, that's my new height, is approximately f prime of a times x minus a plus f of a. Works pretty well. So this equation here, that approximation, is pretty handy. Sometimes we'll also see something like f of x, f of a plus delta x, right? So that would be sort of this new point, right? Well, what's it supposed to be approximately? It's supposed to be approximately, well, f prime of a times, you can write x minus a or delta x. Just for variety, I'll write delta x here, plus f of a. Okay? And that allows us to approximate points nearby. Sometimes that's good enough. I just want to do an example for us real quick. So I put this into Desmos, the square root function. Looks great, right? Well, let's approximate points near 2. And I don't know if you've thought about this, but it actually, like, if you were trying to approximate the square root of 2.4, it would be hard. I don't know that off the top of my head. It would be some work. So let's do this. If you put in the work once and for all to find what the derivative of this function is at 0.2. Now, I know how to take the derivative here, but let's imagine I use this decimal approximation. And now I'm using the equation, right, that the change in f is approximately that derivative times the change in x. So I'm going from here to 2.4, something like that. There's my approximation, 0.141. Here's the actual calculation. You can see I'm a little less than 100th off. that's pretty good. That's pretty good. And actually calculating a line, if you've calculated this number once and for all, it's actually way easier to take this number and multiply by this. Just one last thing that we can do pretty easily in Desmos, I could give you the equation of the tangent line, right? And there's the equation of the tangent line, and you can sort of see what's happening there. You don't have to just calculate the change. You can also calculate the real value by adding f of 2, right? I've added f of 2, and life is great.